Now that we know what a meter, a second, and a kilogram mean, we can go out and make some meaningful measurements of length, time, and mass, right?
Yeah.
Well, the reality is a little more complicated because of significant figures, or Sigfigs. Quick question. Are 5 meters and 5.0 meters the same?
Yeah.
Just like any trick question, the answer is no.
What?
When we say 5.0 meters, we mean the length we measure is between 4.9 and 5.1 meters. When we say 5 meters, we mean the length is between 4 and 6 meters. Clearly, 5.0 meters is more precise than 5 meters. In terms of sig figs, we say that 5.0 has 2 sig figs while 5 has 1 sig fig. Therefore, the more significant figures a measurement has, the more precise the measurement is. The precision of your measurement ultimately depends on your apparatus. In any case, it is the responsibility of a physicist to report the measurements with the correct number of sig figs so other physicists can infer the precision accurately.
Yeah.
To make sure we report the correct number of significant figures, we must first learn how to count the number of significant figures. Here are 4 rules. Rule 1. All the non-zero digits count. For example, 1314 has 4 non-zero digits, so it has 4 significant figures. Rule 2. All the zeros before the first non-zero digits do not count. For example, 0.0052 has only 2 significant figures because 5 is the first non-zero digit, so the zeros before 5 are not significant. Rule 3. All the zeros in between non-zero digits count. 0.001203 has 4 significant figures, so does 2009. Rule 4. All the zeros after the last non-zero digits count if there's a decimal point in the number. 0.0520 and 41.0 both have 3 significant figures. However, these 4 rules do not cover scenarios like 340 or any number with zeros at the end. 340 has no decimal points, but should we count the last zero as significant? We don't know. A number like 340 has ambiguous significant figures because the last zero could be an insignificant placeholder merely to inform the reader that this number is 340, not 34, or the zero could be truly significant. To avoid confusion like this in physics, we often quote our measurements in scientific notation. In scientific notation, a number is written as a times 10 to the power of b, where a is between 1 and 10. This is a rather formal mathematical way of saying it, but in practice we just need to put a decimal points to the right of the first non-zero number and then multiply that number by the correct power of 10. For example, 0.00038 is equal to 3.8 times 10 to the power of minus 4. See how we move the decimal to the right of 3 and then multiply 3.8 by the correct power of 10? So for a number like 340, if we want it to have only 2 significant figures, we can write it as 3.4 times 10 to the power of 2. If we want the same number to have 5 significant figures, what do? Well, simply add 3 zeros after 3.4 because Rule 4 says trailing zeros are significant when there is a decimal point in the number. Note that the powers of 10 don't contribute to the significant figures. The fun doesn't end here though. There will be times when you have to add or multiply different measurements together to get your final measurements. You need to follow 2 more rules to make sure your final results has the right significant figures. Before I show you the rules, I just want to clarify. The addition rule applies to subtraction too, because subtracting is the same as adding a negative number. Similarly, the multiplication rule applies to division as well. Here are the rules. When adding numbers together, we round up the sum so that the sum has the least number of digits after the decimal points. For example, 0.3287 plus 5.1 is equal to 5.4. 0.3287 has 4 digits after the decimal, while 5.1 has only 1 digit after the decimal points, so we round our sum to only 1 digit after the decimal points since that is the least number of digits after the decimal points. This example also shows another important point. If you do your sum vertically and line up the decimal points of all the numbers, you can easily see how many digits should be kept after the decimal points in your sum. In multiplication, round up the product to the least number of significant figures. For example, 3.142 times 4.6 times 10 to the power of 12 is equal to 1.4 times 10 to the power of 13. 3.142 has 4 significant figures, while 4.6 times 10 to the power of 12 has 2 significant figures. The final answer should only contain 2 significant figures. Seeing so many rules for dealing with significant figures can be intimidating, but I assure you that if you do enough exercises involving significant figures, you remember all these rules by heart.